In this video, I'd like to look at some specific examples of the relationship between internal energy, heat, and work. So as a reminder, we can determine the change in internal energy by looking at the heat and the work. So delta U, the change in internal energy, is equal to Q plus W. And we typically divide the universe into the system and the surroundings. And so when we have an increase in internal energy of the system, when delta U is positive, that means the system is either absorbing heat from the surroundings or the surroundings are doing work on the system. Alternatively, the system loses internal energy. It results in a decrease in internal energy or a negative internal energy when the system releases heat to the surroundings, or when the system does work on the surroundings. So let's look at some specific examples of that. Alright, so in these examples, we want to identify whether the energy exchange is primarily heat or work, and then we want to determine whether the sign of delta U for the system is positive or negative. Now in principle, we can define the system however we want. So in each one of these examples, we're told explicitly what the system is. Now for chemical reactions, the system is generally the molecules that are reacting, and the surrounding is everything else. So in the first example here, sweat evaporates from the skin, cooling the skin. And we're told that the evaporating sweat is the system. So we're thinking about cooling and temperature changes, so this is primarily going to be heat. And in this case, the sweat is the system, and so the skin is part of the surroundings. So if the skin is cooling, that means it's losing heat, so that means that the system must be gaining the heat. And so in that case, delta U is going to be positive if it's absorbing heat from the surroundings. Alright, so in our next one, the gas in a piston expands against an external pressure, and we're told that the gas in the piston is the system. So when we have expansion and compression of gases, that is going to be work. Alright, and in this case, the gas in the piston is expanding, right? So the gas is pushing the piston up, and so the gas is doing the work, right? So the system, the gas is doing the work on the surroundings, so the system is losing energy in this case, and so delta U is going to be negative. Alright, if we have an aqueous chemical reaction mixture and we heat it with a flame, so, and in this case we're told that the reaction mixture is the system, right? And I mean, the word heated is sort of a dead giveaway, right? So this is going to be heat, and then heat is going into the reaction mixture, and so delta U is going to be positive. Alright, in our next one, so when we mix hydrochloric acid and sodium hydroxide, and these are aqueous solutions, the temperature of the solution increases. And in this case, we're told that the HCl and the NaOH are the system, and so the rest of the water that makes up the solution is the surroundings. And so the temperature of the solution increases, so the surroundings are gaining energy. That means the system must be losing energy. So the HCl and the NaOH are losing energy when they react, and that's increasing the temperature of the water around it. So this is going to be primarily heat, and in this case, delta U is going to be negative. Alright, and so the last one, when a father pushes his daughter on a swing, and the daughter and the swing are the system, so the father is pushing his daughter, that's going to be work. Right, and the father is doing work on the daughter and the swing, and the daughter and the swing are the system, so the surroundings is doing work on the system, and so in this case, delta U is going to be positive. Alright, and we're going to finish with a little more quantitative example. So we're told that the gas in a piston, and the gas on the piston is the system, is warmed, and absorbs 655 joules of heat. And the expansion performs 344 calories of work on the surroundings. And so I'm going to know what is the change in internal energy. And so one thing we have to be careful of, they gave me the heat in joules and the work in calories. So I have to be aware of the units, and I also have to be aware of the signs that these things should have. So we know that delta U is equal to Q plus W. And so if we consider the heat first, so we're told that the gas is warmed and it absorbs 655 joules of heat. So in that case, the heat, the Q, is going to be positive. So Q is going to be positive 655 joules. Right? If we were told that the gas was cooled or that the gas released heat, then we would know that the Q was negative. In this case, because it's absorbing the heat, the Q is going to be positive. All right, and then when the gas expands, the gas is performing work on the surroundings. So the work is going to be negative. So the work is going to be negative 344 calories. But I can't just add these together because they're in different units. So I either need to convert the calories to joules or vice versa. And we usually work in joules, so I'm going to convert the calories into joules. So I have negative 344 calories for the work, and then 1 calorie is 4.184 joules. And so I get negative 1440 joules. All right, and now that they're in the same units, I can use that delta U is equal to positive 655 plus a negative 1440. And so when I do 655 minus 1440, I get negative 785 joules.